Hello everyone and welcome to NSUCrypto. My name is Nicky Mouha and the title of my talk is Review of the Advanced Encryption Standard. This is work that I am currently doing for NIST. It's a report that should be available within the coming days or weeks. And I'd like to explain to you a little bit about how I approach this subject and what the results are. But first, let me explain a little bit more about myself. So as I explained, my name is Nicky Mouha. I have been working in the field of cryptography for the past now 13 years. I started out doing cryptanalysis. The reason why I started out doing cryptanalysis was because I felt a bit overwhelmed. There are so many cryptographic designs and it was not clear to me what is secure, what is not secure, how it works. So I felt that really studying the attacks would be the best starting point. And when I started looking into attacks, I found that there's quite a significant amount of programming involved if you want to analyze some of the cryptographic algorithms that are being proposed and being used. And it's something that people typically do separately for each paper, for each algorithm that they are analyzing, based on the experience that they've built up so far. Now, I wanted to not only understand those techniques, but I also wanted to figure out ways to make it easier to apply them. This is why, if you look at my PhD thesis, the most cited paper out of this thesis is differential and linear cryptanalysis using mixed integer linear programming. How does that work? Well, mixed integer linear programming is a technique that is used in optimization theory, operations research, and it allows you to solve equations once you specify them. And in this case, the equations that we were interested in solving were ones that show, if you take a cryptographic algorithm, looking here now at block ciphers and hash functions, if you change something at the input, which S-boxes, so these are the nonlinear components of the algorithm, which are going to be impacted by that, which ones are going to have a difference at their input, looking at differential cryptanalysis, and how do these differences spread throughout the algorithm? Typically, you will do an argument where you will say that a certain number of S-boxes are active at least. So a certain number of S-boxes will have differences at their inputs. And this will give you some bounds on differential cryptanalysis because it will tell you what the probability is going to be that you will follow some input difference to some output difference. Now, in the case of the Advanced Encryption Standard, which I will talk about in most of my presentation here, this is where you have a very basic, simple result that says 4 rounds have 25 active S-boxes. And it's something that is actually not so difficult to calculate, but it does require some work. Here, in the case of mixed integer linear programming, I describe a technique that allows you to write out equations and then solve those automatically. These equations, if you write them out, are going to be nonlinear equations, but then I explain how some commonly used techniques can be used to turn them into linear equations by adding some extra equations and variables. And this is a technique that, if you look at designs now, is actually quite commonly used. Not just for differential cryptanalysis, but there is an extension for linear cryptanalysis where the technique applies as well without too many modifications. This is what I was doing in the beginning of my research career. Then at some moment, a company reached out, in this case Hitachi, and they were interested in the design of a cryptographic algorithm. Now, this cryptographic algorithm was supposed to be an algorithm that is the fastest algorithm on microcontrollers. That was the requirement. And they were looking for a message authentication code. So given some input, you're supposed to calculate some tag using a key. You can also see it as a keyed hash function if you want. This was the algorithm they were looking to be designed, and they were looking for really, really good performance on microcontrollers. Now, on typical microcontrollers, the operations that will be fast are going to be the ones that are supported by your instruction set. So then we're looking at operations like additions and exclusive ORs. And also bitwise rotations, because if you only do addition and XORs, then there's no information that goes from higher bits into lower bits. Now, to analyze these algorithms, you're not working with S boxes, so you will need some different types of techniques to do the analysis. This is where in 2012, 2013, I introduced some techniques using SAT solver that allow you to express the way the differences propagate through an addition using a satisfiability formula, and then apply some off-the-shelf SAT solvers to look into some properties. Then, as my research career continued, I was really fortunate the company decided to pursue the standardization of the algorithm. So this is how, as you can see now, I started with cryptanalysis, rolled into design, then rolled into standardization. When I rolled into standardization, I was really fortunate to have a different perspective that people might have who are doing standards from the very beginning. Not just because it was an algorithm that I was personally involved in as a designer, but also because I had a longer background of cryptanalysis and design so that I could better understand some of the decisions and trade-offs that were being made, and found this to be really an exciting experience to go through. Now, as I went through all of these different steps, different life cycles that you have for a cryptographic algorithm, I had a huge amount of discussions with many different types of stakeholders involved. And this gave me a good understanding of how cryptographic algorithms are being analyzed, how they're being designed, and how a standardization process works. And this is some knowledge that I would really like to share with you guys, and also show how it could be applied to understand better the standardization of another cryptographic algorithm. Now, the one algorithm that is going to be the center of this presentation is an algorithm called the Advanced Encryption Standard, standardized in FIPS 197. And the Advanced Encryption Standard is perhaps the most widely used block cipher in the entire world. You will see, for those who are new to cryptography, that if you go to your browser and you click the padlock to see what is secure in the connection, AES will appear there. You will also see that if you're using Wi-Fi signal to connect to the internet and you look, oh, what's the security for Wi-Fi? AES will appear there as well. And even in things as garage door openers or badges to enter doors, you might find AES as well. So it's really a ubiquitous algorithm with a lot of different use cases. And interesting to look into how you would review such a standard. Now, NIST, I'm currently working at, commits itself to regular review of cryptographic standards and has launched a process to start the first analysis of its standards. And this first one is going to be the Advanced Encryption Standard. So that's the subject of this presentation. Now, another work that I'm doing in parallel, which will come out sometime later, is an analysis of the block cipher modes of operation. Because when you're using a block cipher, it supports only short input, but in practice, we might need to support longer inputs and we might need different functionalities as well. So actually, a lot of the requirements that you might have for a cryptographic algorithm, you might only see at the mode level, not at the block cipher level. So this is something that, for those who will see the report in the upcoming days and weeks, is an element that is moved to a later review to see how the block cipher modes are handling this. But let's go back to this first review to AES and say a bit more about the algorithm. AES is designed by Johan Dame and Vincent Reyme, two Belgian cryptographers. You might be surprised, like, how does this end up being the United States standard and the de facto worldwide standard for block cipher? Well, what NIST, the National Institute of Standards and Technology, did is launch a worldwide competition around the year 2000 to standardize a new block cipher to replace the data encryption standard, or its later iteration, the triple data encryption standard, and to be used instead of this older algorithm that still dates back to the 60s and 70s. NIST organized an open competition. Everybody in the world could submit their design. It was a really exciting moment for people of all kinds of backgrounds to look into how a standardization process works. A lot has been said about this. Many reports have been written about this. And it's seen as a stellar example of how NIST can do development of a standard through an open competition process. After that, several other organizations have looked into copying similar processes where they're looking into how would you come up with a new standard. And in this competition process, a lot of requirements were already written out at the time to make the competition fair, to make it open, have later been clarified and established again. And that is seen as a golden standard for designing and for standardizing a cryptographic algorithm. And what you might want to do is, in the context of a review of a standard, to go back at the competition, to look at the requirements that were imposed there, things that people found to be interesting, reports that were written. So these are reports that are now 20 years old, and see whether some of the conclusions that were made there are still valid, are still applicable to algorithms as we are using them today. At that time, people were focusing a lot on how AES is being used, can be used, and where they might appear. In the context of a standards review, it can be interesting to see which other standards reference AES. I already mentioned the block cipher modes of operation, but you will see AES appearing into different contexts as well, because this gives a better indication of whether something is secure or not secure. That brings me to my last bullet point here. The most important feedback that I received as I was working on this review of AES at NIST was to focus on attacks. And by attacks, the idea is focus on properties that make the system, that make the algorithm fail in practice, that can cause real or potential problems when it is deployed in practice. So in that sense, you're actually not just describing theoretical properties about the algorithms, but you're also indicating how those theoretical problems might have a potential impact on the practical use of the algorithms. I think it's something we're actually not doing enough in the research world, in the cryptographic literature. And it can make it a bit confusing. You might look at a paper that is describing some property of a cryptographic algorithm, and it's not easy to understand whether this property will or will not have an impact on the way that the algorithm is being used. But this also gives, I'll discuss this more in the later slides, this also gives an opportunity to look at how do you move from cryptography, which historically used to be more of an art, more of a black art, how people were designing algorithms, more into an engineering practice, into a scientific practice. You can perhaps not turn everything into strict mathematical rules. There's also some consensus necessary of what people consider or do not consider to be a good enough algorithm, secure enough algorithm to use. But this is not just an opinion of experts who look at this in isolation. Actually, you can break down each of these standards, each of these algorithms into components, into building blocks, and get an understanding of what each of those components is supposed to deliver, whether they do deliver it, and whether they should deliver it, whether it is necessary, linking back to properties of the algorithms used in practice. So this is something that I see as the main evolution in the past few decades and years in the field of cryptography, moving it into a scientific discipline and getting a better understanding of how the algorithms are being used. That is also one of the main focus domains of this analysis, this review of the AES encryption standard. Now, if you look at a review, there are different ways in which you can review an algorithm, different perspectives that you can have. Namely, you could say, let's just look at a decision. That would be like a managerial executive level, just like renew or not renew. If you're not going to look into the details, you might actually not be interested in more. However, if you're also going to deploy a standard, implement the standard, you might be interested in the editorial side of a review. So you might want to know, given a standard, is this standard a concise standard, a complete standard, an unambiguous standard? Does it contain some types of mistakes that might make it open to interpretation? Perhaps even some things that are incorrect. For people with background in cryptographic design and cryptanalysis, they might have the most interest in technical review. So they would like to know, is the algorithm cryptographically secure? And that is something you might not see just by looking at the standard itself, because there it will just describe mathematically how the algorithm is working. But it will be clear when you see how a standard is being used, how it's being implemented. So that's another thing that we knew already during the AES competition and is becoming even more relevant now as we are re-evaluating how the standard that exists now, that has been deployed for 2 decades already, is used in practice and whether there might be issues to the way that it is being used. I'm going to move on to explain what types of resources you might consider if you want to analyze a standard. So I tried to explain the previous slide. If you're going to look at a standard in isolation, you might really not find so much. It would be interesting to see, for a block cipher, how do you use it in certain block cipher-based modes of operations? These would be the higher level operations, in which schemes you are using them. So a scheme is a simple protocol where you're doing something like key exchange, for example. 2 parties, cryptographers like to call them Alice and Bob, who want to exchange a cryptographic key. And if you look at higher levels, you might want to say, well, given the specification on paper of what an algorithm is, how can you check, given an implementation, whether the algorithm conforms to the standard, and further on, whether the module, so this calls an implementation a module, whether the module is secure as well. So then you look at properties where the key needs to be secret, how that key is being kept secret, following the lifetime of the key, making sure that the key cannot be extracted from the device. Other documents look at configuration guidelines. So it's interesting to see, for the example that I mentioned earlier with the padlock you see in your browser, TLS, Transport Layer Security, NIST has a recommendation document explaining how to configure TLS for systems used within the US government. Many people adopt these configurations voluntarily as well. So in these configuration guidelines, you can get even more information that might indicate whether certain assumptions you made about how you're going to deploy a particular primitive higher level operation scheme, even when it's implemented, are used securely or not securely at a protocol level when you want to access your bank's website. And then another NIST maintains resource is the NIST National Vulnerability Database, NVD. And interestingly, in many cases, when you're looking at NIST taking action with regards to a standard, there is a particular vulnerability. These vulnerabilities, they are numbered using CVE numbers, Common Vulnerabilities and Exposures Enumeration. This is a test that MITRE does. US Research Institute, and then NIST has takes over the information from MITRE when new vulnerabilities are added to the numbering scheme, and evaluates as part of this vulnerability database what the impact is of these vulnerabilities to try to have some level of scoring so that people can see when they're deploying systems how serious a vulnerability is and how which actions can be or should be taken in response to a vulnerability. And those types of vulnerabilities, they might actually impact some of the cryptographic algorithms that we are using. So an example here, this also shows the right column of my slide. We have a lot of publications available and all types of emails, comments that the public have. In this case, there is a paper, just to give an example, that describes how you can cause internet connection, browser connection using TLS and using the triple DES block size because of its 64-bit block size to cause vulnerability and an exploitable vulnerability in the way that the algorithm is being used. And then this resulted not only in an academic publication, but also in a vulnerability number. And at that moment, companies took action and figured out ways to reduce their exposure to triple DES and the security impact of still using this old algorithm. But that then also was used as feedback for NIST to say, hey, is triple DES still an algorithm that is secure as we have it standardized now? And is it something that can be used as a general purpose block cipher cryptographic algorithm? And a decision was reached to say no. So now it's not just the case that the standard of triple DES has been updated to limit the amount of data that can be processed per key, but also that a decision was taken to sunset triple DES and to stop using it. So this is a separate case where you just look at one vulnerability and you see how it moves its way all the way back to the standard. In this case, also block cipher. NIST has currently 2 block cipher standards, triple DES and the Advanced Encryption Standard, which I will talk about here. And it's interesting to be aware of these types of procedures, the way that something can move throughout this maintained landscape, because there might be other things that we want to be aware about and see how the standards can be improved, can be better explained, how we can move to the future. Here I'm showing how if you look at a standard in isolation, you might not, right, there's a lot of repetition in my explanation, but it's the point I really want to stress, right? If you look at a standard in isolation, you're typically not going to find so much. It's about the standard, but also how and where the standard is being used, about the context of the standard. So implicitly or explicitly, a standard or guideline will have some guarantees that they are making about what the algorithm is supposed to offer. In the case of AES, you can say block cipher, but it even goes further. NIST was looking during the AES competition for what is called a pseudo-random permutation, an algorithm for which for any input, the output is going to follow a random distribution, is going to look randomly. And this is what block cipher-based modes of operation rely on for the security in their construction. So that is a kind of guarantee that the AES standard is making. On the other hand, if you look at the context, the place where standards are being used, then there are assumptions about what the standard is offering. And there might be some mismatches in there when those are not fully explained or fully understood. So I see this in general as an example of how we can do progress in the sense of further moving cryptography out of the early days when we were not so aware of how you can split cryptographic algorithm, cryptographic protocol into different building blocks, different properties, what they were supposed to offer, and how we are today understanding the requirements implicitly and explicitly formalizing what those standards are supposed to guarantee, what they are actually guaranteeing, and what is being assumed in other standards. Let me give an example, because I think so far this has remained quite vague. So here is a very simple example, the simplest example I could find in the NIST standards of AES being used. So how does it work? Well, if you are working at the US government, then you will have a badge, smart card, a chip card, that is called a PIF card, that everybody has, everybody needs to carry around, and that you also use to log into your computer. So in that case, you don't need to use a password. You can use your card and your PIN code to log into your system. And with this card, AES is being used as part of the PIF authentication protocol. NIST has a standard describing how PIF cards work, and also has an explanation of how this authentication protocol works. And it is using AES in a block cipher-based mode of operation that is called ECD mode, electronic codebook mode. But actually, it's a bit of a shorthand of saying it is using AES directly, because we're only using it on an input that is the same size of the block size under a secret key. Why do I think this example is interesting? Not just to keep the eye on the ball, to see how is AES being used in practice, but this actually allows us to explain why this randomness property is required and how this randomness property is used in practice, what it means. So as you can see here, first the card needs to wake up. So the application software is sending a request challenge command to the card. And then the card will send out a challenge. This challenge is a random number to the application software. And the application software, it knows the secret key that is inside the PIF card. So using this secret key, it can encrypt the challenge to obtain a response, sends the response back to the PIF card. Then what the PIF card does, according to the standard, is it takes the response, decrypts it using the same key, and then checks whether it was the challenge that was being sent out. If that's the case, it will say okay. If that's not the case, it will say error. Okay, so what's going on here? If you're looking at this protocol, it is supposed to be that the PIF card wants to know if the application software knows the key or doesn't know the key that is stored there in the PIF card, to know if the application software is authentic or not, to be interacting with the PIF card. So you could implement it in a simple way. That's not how it's done. By just saying the application software sends out a command and says, hello, I'm authentic. Because if it would do that, then we could intercept this message and just replay it again from application software that is not authentic. So this would be a case of bad use of static credentials. That's not the way it's being done. The way it's being done is the application software gets a challenge. This challenge is supposed to be different every time that the protocol is being used. And in this case, even if you are presented with a large number of challenges and a large number of responses, because we could put this application software on a workbench and then see if it is behaving the way we would like it to behave, it should not be possible for somebody else, just with access to these challenges and the responses, to figure out what the response is to a challenge that has not been seen before. So this shows us why we need this randomness property and why resistance against, for example, differential cryptanalysis is important. Because let's say that we are looking at the next challenge. The next challenge might be just like incrementing a number by 1, to make it simple. The challenge can be chosen any way you want to choose it, because it is here checking the application software whether it's replying correctly. But let's say we do that. We just do a challenge and then we add 1. That will introduce a difference in 1 bit of the input challenge. And then we want to know what is going to be the impact of that on the response. If we see that the response will not follow a random distribution, will actually have specific bits that are not going to be changed, then this helps us to predict the response, and this makes it easier for us to try to come up with a response without knowing the application software. There are a few interesting aspects here as well. One is that obviously if you know the key, then everything is broken. So it's really important to keep the key secret. With knowledge of the key, you can just compute every response to a challenge that you've never seen before. It's also interesting to see how the PIF card is decrypting the response. It could also have encrypted the challenge. And it's interesting to see how there might be problems with this system if, for example, let's say the challenge is too short. That will impact the security of the system, even if the block cipher is completely fine. Because when you analyze security in practice, it's not just how you look at the components, but it's also how they're being instantiated, how they're being deployed. This is also a level where you might see attacks resulting from an insecure or unprotected implementation. If somehow timing information is leaking something about the computation, if somehow we see that the power consumption is leaking something, if there's some way in which we might extract some information through a side channel or through injecting a fault, then this might also help us to break this protocol in practice. And that's actually explaining why there is so much guidance explaining how to do a secure implementation of a cryptographic algorithm. So these are things that were already considered during the AES competition. How secure is the algorithm against side channel attacks? And are interesting to reconsider now that we look at the algorithm again during the review of a standard. So this is how I'm trying by example to motivate again how when you want to analyze a standard, we should have a holistic view. Let's look at everything we looked at during the AES competition, where most of this was already considered, and look at it retrospectively. But let's also see how it is being used in practice, because that helps us to see whether there might be issues with regards to practical attacks, if a property is only of theoretical interest, or if it's actually potentially a practical issue. Now, I think many of you will be looking at what is the outcome of the review, but there are so many different things to be considered. And the document, if you will have a look at it, is actually explaining a lot of different details, clarifying some things that previously were perhaps clear, perhaps not clear, but deserved some further investigation, looking into attacks that were looked into before. I will not go into all of those details here during the presentation because this is looking at it at a lower level. But I want to highlight a few things. So the security model of how we look at an algorithm has become a bit different today compared to when AES was being designed as a cryptographic algorithm and being standardized. For example, related key security. So this means that the attacker does not know the secret key, but knows some relation between two secret keys, which is relevant in certain protocols that are used for key establishment and key exchange. This is a property that was already considered at the time, but not so well understood yet from a theoretical point of view. Now we have a much better theoretical understanding. And now we also see that in the case of AES, The full AES is, in the case of the 192 to 56-bit versions, vulnerable to related key attacks. So this is something that is interesting to explore, to discuss, to look into. For some protocols, this might cause an issue. For others, it will not cause an issue. So it's indicating it's not just the algorithm, it's also how it's being used. There are other aspects that we will look into as well. Here, I just give a brief overview of some issues, but I will not go into too much detail. For those who are interested, I really encourage you in the coming days and weeks to have a look at the report. Some takeaways here are not just, as I mentioned in the previous slide, that related key attacks are an issue, but also that bike leak attacks, which are basically attacks that use exhaustive search, but exhaustive search on a reduced number of rounds of the algorithm. AES has 10 rounds, this will be exhaustive search on a smaller number of rounds, have also been found for the full AES. So this allows you to have some small speedups in certain models on exhaustive search. It's another thing that is interesting to comment on and see what it means, refine the model related to the Advanced Encryption Standard. And actually, people have analyzed AES in various situations where they look at known keys, chosen keys. There's discussion about that as well. I mentioned already a bit number of rounds. I think that's something that is really interesting and important when you are looking at the design and standardization of a cryptographic algorithm, and one that I personally did not understand so well as I was working on it. I used to think, in the case of Chaskey, that the number of rounds is something that is determined by the designer, because as a designer, you are saying what you feel comfortable with, and you should not be designing an algorithm that you yourself don't feel is a secure algorithm, so you need enough rounds for you yourself to be comfortable with the design. However, if you look not just at historical examples, but also at the standardization of Chaskey here itself, the number of rounds initially proposed was 8. The standardized variant is 12. This is the result of many discussions that were held with a lot of people who are experts in the area, going through the standardization process to indicate what they felt comfortable about with their understanding of the algorithm, what they felt comfortable about with their understanding of the security on various types of platforms. Because you can always increase the number of rounds, but it's going to make your algorithm slower. That is not always what you want. So the number of rounds is one of those items that is discussed as consensus that you form among the community about what you want for a cryptographic algorithm. In the case of AES, AES has either 10, 12, or 14 rounds for the 128, 192, or 256-bit versions. And then if you start to look at attacks on AES, let's look at the 10-round version. Then if we don't exclude attacks in special key settings, we just have a single key that is chosen at random. And if you don't look at these bike leak attacks and do some small speed up over exhaustive search, and what we find is the best attacks are on either 6 or 7 rounds, depending on the settings that you're looking at. And those are attacks that would then give a security margin of, let's say, 3 rounds. A question is this a security margin that we are comfortable with? Is it too big? Is it too small? Is it enough? And it's something that has already been considered during the standardization process of AES and was discussed at length in the reports that were written there. Regularly, questions come up of people asking, should perhaps the rounds be increased? Should perhaps the number of rounds be decreased? Now, there are advantages and disadvantages to all of those. However, I think the report as it stands now is indicating that if we understand now that the best attacks are on either 6 or 7 rounds, and we look back at the report that was written in 2000-2001 on the AES competition, it also mentions that the best attacks are on 6 or 7 rounds. So quite surprisingly, even though the models of attacks has changed, the security margin has remained virtually the same, or the same, let's say. And the considerations that were being made at the moment that AES were standardized about the security still seem to hold, as we are looking at the algorithm now, 20 years later. So in the report, you will also find a lot of minor editorial feedback that don't amount, I think, to items that are sufficient enough to update the standard. I think the standard is clear the way it is written. However, there are some things that you might want to improve if you want to especially make it more concise or explain some more difficult points. So I think the standard, the document, the standards review is setting a good basis to recommend to renew the standard. And this is, I think, the most likely outcome. But don't look at the decision by itself, because that is just one element, right? I think the focus should be on making a lot more explicit about what the algorithm is, what it's supposed to guarantee, how it's being used, what types of attacks exist, and to get much better understanding of the algorithm that we are dealing with, and to look at this into a broader context. It's actually in that broader context that things like, for example, security against side channel attacks and against fault attacks, so the secure implementation of AES, can be a problem in practice because it's not such an easy thing to do. It won't change the standard by itself, but it has some impact on other related documents that explain how AES is being used in practice. To conclude, I'd really like to reiterate, because I think that is the most important point I wanted to make here. Let's try to understand the assumptions of standard. Let's try to see how we can make them implicit when they were explicit, when they were implicit. And let's also look into other places where standards is being used to understand, when we look at the standard, what those types of assumptions are that are being made. And let's focus on attacks. This is something that in many cases is not so difficult to do, but often not done, because it's also seen as not necessary when you look at standards that are, when you look at cryptographic papers, because it's enough to explain that some theoretical property is problematic about an algorithm to get a publication. But then it makes it difficult to know, is this actually impacting or not impacting an algorithm as we use it in practice? So in those cases, I have done some effort to link back in the standards review and also in this presentation how some of these can have impacts on what you are using. Lastly, I would like to wish all of the participants of NSUCrypto 2020 good luck, and thank you all for listening to this presentation. Thank you very much.